So next here we're going to talk about intermolecular forces and their boiling point / melting point and how they affect that of a pure substance. So this is not mixtures. So before we had mixtures, we had stuff dissolving in other things. That's going to be the only time this occurs in this chapter. Only with solubility. From now on, it's just pure substances. When we're going to talk about, the boiling point, melting point, later the vapor pressure of mixtures, that will be the next chapter. So right now, this is just like, pure water or ethanol or acetone or, whatever it might be, octane, anything like that. So just the substance by itself. And so first off, let's just make sure we're on the same page. You probably know what boiling point and melting point are, but just to make sure we're there. So the boiling point is the maximum temperature that a liquid will reach during evaporation. So the boiling point of water is 100 degrees Celsius, at least, standard temperature, standard pressure and everything like that, 1 atmosphere. You change the elevation, you change the pressure, the number can move, but there is a maximum temperature you can reach. And then it starts to boil. You start just getting more gas forming. You add more heat, it just starts boiling faster. It starts forming gas even faster, but it doesn't get hotter. And so that's what the boiling point is. The melting point is just the temperature where a solid becomes a liquid. So, melting point of a chocolate bar is somewhere between room temperature and your pocket, right? Because it melts in your pocket. That's why M&Ms were made, by the way. You put the candy coating on the outside, and then you don't get chocolate everywhere, so you can, leave them on the dash of your car and they melt, but then they turn back into M&Ms. Amazing technology, those M&Ms. But what we have is a solid turns into liquid, it melts. So that is the temperature. That occurs at a set temperature, whereas evaporation's a little trickier. We're gonna have another section where we talk about it a little bit more, but it's occurring at temperatures below the boiling point because of what's called vapor pressure. But we'll talk about that in the next video. So we'll have a vapor pressure video. This is just about boiling point and melting point. So there's this temperature, and it can move, it can change with pressure. Our boiling point can change with pressure, as we talked about. But every substance can have a set boiling point at, say, 1 atmosphere. And intermolecular forces will affect that. So what the substance is will change what that boiling point is. For example, we're surrounded by oxygen right now. It has a boiling point. Maybe you watch the video of liquid oxygen going through the magnets. Well, it's always a gas when we see it for the most part. I'm experiencing oxygen gas right now. So it has a boiling point that is well below room temperature. I have to get it very, very, very cold to be a liquid. And there's a freezing point or a melting point where it becomes a solid. It's the same temperature. It just depends on which way we're going. Are we freezing it or are we melting it? Same temperature that it occurs though. All right, so that's what these are. And then the trend is very straightforward. The stronger the intermolecular forces of our substance are, the larger the boiling point is going to be, and the larger the melting point is going to be. They all fall along with each other very nicely. So if we have stronger intermolecular forces, it means the molecules like being close to each other. There's a lot of attractive forces holding them together. They're really kind of hugging in there. And as we melt something, we're moving them away from each other. And when we boil something, when we turn it into a gas, we're moving them very far away from each other. We have to separate them. And so the analogy, and I came up with this analogy actually the first time I taught this class, this section of this class off the top of my head. I used to play a lot of basketball when my shoulders would let me. And there's kind of a classic thing that happens in a basketball game where if someone tries to get in a fight, everyone holds them back. It's not hockey, you don't just let them go at it. We're not wearing pads or anything. Like, you can kill each other in basketball. Like, you're trusting everyone around you every time you jump in the air. But, something happens, you gotta look tough. You don't really want to fight, but you gotta look like you're gonna fight, and so everyone holds you back. Everyone knows, it's like a little dance. Every now and again, people get loose and they actually fight. It happens. But when they're being held back, I consider that the liquid phase. Everyone's moving around, but they're stuck together. The second that player gets loose and the other player gets loose, they've popped off into the gas phase. They are now freely moving around in space, and then they will collide. That's what happens. That's the difference between gas and liquid. And solid is, I don't know, like when a cheer team forms a pyramid or something, I don't know. Everyone lines up for the free throw. You're in a set position in a set location. There's a lot of you know, I guess you could make an analogy to baseball's a pretty solid sport. Everyone's kind of in their spot. Not a lot of movement happening all the time. You're at the base, everyone's at their base, at their defensive location, pitcher's on the mound. Even the umpires don't move that much. So that'd be like a solid, I guess. All right, and so this trend, you know, more intermolecular forces. So if something hydrogen bond, it's going to be a solid more easily. It's going to have a higher melting point. It's going to have a higher boiling point than something that doesn't. And so, for example, if we were to compare, say, you know, water and methane. I've been leaning on these Lewis structures a lot in this course, so why not continue to do so? We got water, we got methane. Well, we look at this. This is an OH bonding machine. This is going to have higher melting point and boiling point because it can H bond, which equals larger intermolecular forces. Okay? That's what we're looking at there. And that's just kind of the trend that holds. You can just look at, you know, does it have more attractive forces or not, or intermolecular forces or not? And you can just determine roughly in comparison. We're not going to calculate exact boiling points or exact melting points. You're just going to compare and contrast which one would have higher or lower. That's the main thing. And just this general trend and why we have that general trend. These molecules, they like being close together. If they have strong intermolecular forces, they are very strongly attracted to each other. You know, they have dipoles that will attract versus, you know, dispersion forces that will only kind of attract. And then hydrogen bonding, which is really, really rock solid, really attracts. So keep that in mind as you work through this. All right, so next we're going to talk about vapor pressure. So that's going to be purely moving between liquids and gases, and it's still only going to be for pure substances. Next chapter, we worry about mixtures, not this one. All right, so vapor pressure's coming right up.